Okay, the next criteria that we're going to use to determine the relative acidity of molecules is dipole induction. And the basis of this category is that electronegative atoms can help stabilize conjugate base through inductive effects. We just talked about how that negative charge in a conjugate base can be distributed through the molecule through resonance, through pi or p orbitals. But now we're going to show how they can be shared, how that negative charge can be shared through sigma bonds, through inductive effects. So let's look at an example of how dipole induction can work. So here we'll just look at two different potential acids. Here we have, let me see, our conjugate or our acetic acid here that we showed on the previous slide. And we're going to compare it to something a lot like acetic acid, except it's got a chlorine in there. Okay. Let's put the lone pairs on our oxygens just to be clear. Now, just like when we were discussing resonance, we're going to draw out the structure of the conjugate base for these molecules and try to figure out how stable those conjugate bases would be in comparison to each other. So here, the only difference is the presence of that chlorine instead of a hydrogen. And the negative charge is still on one of these oxygens. Doesn't matter. Hopefully you recognize there'd be resonance, and this negative charge would be shared through resonance with both oxygens. But that wouldn't explain a difference in acidity between these two molecules because they'd both be stabilized through resonance. Really the difference is the presence of this electronegative halide. Now, does the presence of this electronegative halide make a molecule a better acid or a worse acid? Well, if it's electronegative, it's forming a dipole, right? And through inductive effects, it's drawing electrons towards itself. Now, would this stabilize or destabilize this conjugate base? Well, if we have a negative charge in the conjugate base and we have sort of a vacuum cleaner for negative charge, help pulling it through these sigma bonds, distributing it throughout the molecule, that has a net stabilizing effect. Right? The chlorine wants these negative, the extra electron density. It wants that negative charge, and if we provide it in this conjugate base, that's a good stabilizing effect. This acetic acid doesn't have that negative charge vacuum cleaner, and really this negative charge is stuck out here on these oxygens. It's not going to move through these single bonds because there's no electronegative atom in the molecule in order to stabilize it. And so if we're to compare these two as acids, this is still, it's a carboxylic acid functional group, so it has a pretty low pKa of 4.75. But if we have this chlorine to it, then all of a sudden we're 2.81. If we substituted the chlorine for a fluorine, would that make it an even better acid or not so good? Well, fluorine's even more electronegative than chlorine, so it would do a better job of drawing that negative charge throughout the molecule through inductive effects. So if we have a fluorinated acetic acid, we're a little better. We're at 2.66, a little more acidic than the chlorinated version. Okay, the last criteria we're going to look at when we're thinking about relative acidity is, or actually we have two more, right? We have orbitals. We're going to look at different orbitals, what orbitals are present in the conjugate base. And this is, again, a pretty simple concept. If we have a negative charge present in our conjugate base, if we can draw that negative charge closer to the nucleus of an atom, then it's going to be more stable than if it's further away. So when we think about the different orbitals, we're really thinking about the hybridization of the molecule. Are we S? Are we sp? Are we sp2? Are we sp3? And if we want, the negative charge of our conjugate base to be closer to the nucleus, then really we want our hybrid orbital to have the most S character as possible. If you remember our S orbital, this looks like a sphere, right? The p orbital is, or maybe a dumbbell. And for the s orbital, those electrons tend to hang out closer to the nucleus, more stable. So the best would be S, then sp. The more p character we add, the more we're moving that negative charge further away from the nucleus and destabilizing it. So let me give an example of this. Here is a, pretty honestly terrible acid. We've got ethane, right? We can compare that to benzene, and we can compare it to acetylene, right, where we have a triple bond present between the carbons. Now, again, when you're considering acids, you really need to consider what's the stability of that conjugate base. So here we would have a loss of any of the protons. Here we would lose a proton here, right? And for acetylene, we could choose either one of these protons to lose. Now, both, all of these are on carbons. This might be resonance stabilized, but if we think about the different orbitals present here, what's the hybridization of the carbon here? Well, this carbon has 4 groups of electrons around it. This would be an sp3 conjugate base around this carbon. This one has, a double bond here, so we can think of this as only having 3 electron domains, sp2. And of course, this triple bonded carbon at the end would have 1, 2 electron domains and be sp. And so according to our orbital theory here, this negative charge on this conjugate base would have electrons closer to the nucleus, more stabilized because of the hybrid orbital having more S character. And so we would predict that this would have the highest acidity and this the lowest acidity. And none of these honestly are very good acids at all. This has a pKa of 25, but this is worse with 42, and this is terrible at 50. It's very difficult to just rip carbon-hydrogen bond apart to leave a carbanion as a conjugate base. Okay, our final consideration is going to be solvation, right? Solvation has to do with solvent, and you probably remember this from introductory chemistry, that if you have any charge in a solvent, whether it's because an ionic salt has dissolved in water, that the solvent may have the capability to solvate or stabilize those charges. Let's look at an example in water where we have, let's say, sodium chloride, right, an ionic compound dissolving in aqueous solution. We form our sodium plus and our Cl minus. Okay. These charged ions can be solvated or can interact with the solvent in a way which stabilizes them. And let's imagine how that happens. Let's say we have a positive charge sodium in water. Well, water is a polar molecule. That means it has a dipole associated with it, a partial positive charge, a partial negative charge throughout the molecule. And so that water may orient itself in a particular way to sort of give our positive charge a nice big hug. In this case, I'm orienting the oxygens, the partial negative charge on that oxygen, towards the positive charge of my ion. And what we've done is really spread apart the positive charge of our ion and shared it with the solvent, right? The same can happen with a negative charge, like a chloride. In this case, the more partial positive part of our polar solvent, the hydrogens in this case, would orient towards the negatively charged ion and again spread the pain of that charge, share it with the solvent. So instead of a pinpoint negative charge on a chloride, now it's sort of shared in a larger area, and that has a stabilizing effect. Now, how does this pertain to acidity? Well, you might have already seen it. Often with acidity, we're forming negatively charged conjugate bases, and we've already talked a lot about how if you can stabilize that conjugate base, you end up with a better acid. So let's take an example here of maybe a couple alcohols. Let's look at this one. One propanol, and let's compare it against two propanol. Okay, both have similar atoms, similar number of atoms, but there's a difference in acidity between these two. And the difference in acidity is based upon the stability of their conjugate base in the presence of a solvent. Now, if we consider the conjugate base for each of these, they both would have a negatively charged oxygen. And the only real difference is the branching between these two conjugate bases. Now, the branching tends to decrease solvation. And you might think of why that would happen just from a physical basis. If the solvent really needs to nestle close to the negative charge, wrap itself around it, give it a big hug in order to stabilize it, if you have branches of methyl groups or other things around that negative charge, there's going to be some steric hindrance. These carbons are going to get in the way of the solvent and prevent it from orienting and organizing itself around that negative charge. Well, if the negative charge on this molecule is sort of hanging out at the end, that's much more easily solvated and easily stabilized. And so if we were to compare the acidity of these two molecules, we'd say, well, they look really similar. The only difference is their branching pattern. Now that's going to make this much more difficult to solvate. It's going to destabilize the conjugate base. Therefore, this molecule is not going to be as good of an acid as this one, which would be able to have a more stable conjugate base. And so that would be a comparison you could make between two similar alkane or alcohols that just differ based on branching patterns.